Okay, we'll start a new session, session 10, which is linear map and matrix. This is going to be a bit more faster session, I think, to talk about that matrix is something more than just something you use in equations. And I'm going to talk to you about why it's some sort of special linear map and what linear map is, of course. And then after that, I'll just give you some very nice notation that you should know about some matrices, because matrices have very many properties that you might need to know about, like square matrix and other many properties that you should know. So we're just going to talk briefly about that, okay? Yep, matrix is also a function. Not surprising, actually. A lot of the things are functions in math. So why do you use matrix, okay? As I said, there are some convenience that matrix gives us, like the one we used, how we could make the Lorentz system equation into just one line. That's one way we use matrices, and also very important. But also, actually, we use matrix because matrix is also sort of a function that has very nice properties. So actually, it is a function mapping one vector space to another. So remember when we talked about functions, we talked about function as if like it's a function that maps one space to another space. Analysis, so we talked mostly about like function mapping real numbers to real numbers. Well, actually, matrix itself is a function that maps vector spaces into vector spaces. So let's talk about this. All right. So think about some m by n matrix, and we're going to call this to be matrix A, okay? Now, we're going to think about two vector spaces, U and V, where U is Rn and V is Rm. So what does that mean is that, so we have a vector space where, let's draw from here. There's a U, which is Rn, and there is a V vector space, which is Rm space. So real numbers, right? As I said, like multidimensional R spaces are basically vector spaces, so we can think about that. So in this case, then we can say that some vectors such as from x1 to xn is going to be element of U, and x1 to xm is going to be element of V. Note that I kind of changed the definition, notation for vectors, but they're the same thing. You can write the vectors as a column way, which is like column vectors, but you can also just write it like this way, which is like you just write like a row. It's like a coordinates. It basically means the same thing, okay? So in this case, then we have that x1, xn it's like an element of U, x1 to xm are element of V. And note that if we just put the n tuples in a vertical form, it's just like, you know, as I said, n times 1 and n by 1 vector spaces, right? So we're going to show that the matrix A is just a function mapping Rn to Rm. So we have a matrix here, A, which is basically a m by n matrices, right? So what we are showing is that actually this A, what it does, it maps elements here to elements here. It's a function. And we're going to see how it turns out. We're going to show that the matrix A is indeed a function. So first we're going to define matrix as a function here. So, well, we can define the function matrix such like this. So y is ax, right? And you can kind of see this just similar notation for function. So instead of writing fx, right, the most familiar way to write function, we started writing ax for just function matrix, right? So in this case, y is Rm space, and x and the input part is Rn space. So we put in the Rn, and we get this element in Rm, right? You can kind of see that it kind of holds because elements in Rn, they're kind of also like a matrices, right? So basically what they are is that we have an n by n matrix in the middle, and we're multiplying it with m by 1 matrices, but now we call them vectors here. This is vectors. Well, also could be vector spaces, I mean matrices. If we multiply them, we know that matrix multiplication gives us a vector or matrix such that is m by n matrix, right? And this is just the element here. Right? So what this does is that basically matrix maps the n by 1 matrices or n by 1 vectors into m by 1 vectors or matrices. Okay. So that's what the notation says. So in that case, matrix is like a function. going to give some example here. For example, I'm going to do some computations here, right? We're going to define A as that. So we had this case. So what we're doing is that we're giving an example. I'm going to write A as, what did I write? 1, 2, 3, 3, 4, 5, and 1, 1, 2, right? Okay. So in this case, M and N are all 3 by 3 matrices. Okay. So then we can kind of see that this function has to map R3 space into another R3 space. So it just maps same spaces. So let's see how it does it. For example, think about multiplying this with, let's just say this element is 1, 1, 1. Okay? So we're having a 1, 1, 1 matrix or vectors here. Multiply these two, right? And you just do multiplication of matrices that, like I told you, what you're going to get is, you first do this, right? First row and first column, so it's 6, right? Second row, first column, so it's 2 by 1, so it's 12. Yeah, thank you. So, and we have 1, 1, 2, and first column we have 4, right? So so this is A, and this part is X. Remember, this part is Y. So we multiply the matrix, and what we got is another vectors in our R3 space, which shows that it mapped one element to another, right? Second example here. All right. So, in fact, even though matrix is a function, we have a special name for this kind of functions, and we call them linear maps. You might be surprised by the new name, but they're just the same thing. Linear maps kind of like, we sometimes call function this concept as map. So like they're basically very similar. When you say linear map, it kind of means like linear function, something like this. Although it's not a linear function as in like the one you're very used to. Like 선형함수 이런 개념은 아닌데요, in Korean. So, but still, it has a very linear quality, so we call it linear map. So what this means is that there's a definition here. So we have two vector spaces V and W over the same field F, okay? And most of the time, a lot of these vector spaces, they're going to have the same field, okay? So we have a map, or a function, so we call it. There's a function T, or map T, from V to W, called linear map, if for all U and V, and scholars, these properties hold. So what is happening is, now we're having a case, did I write W? Okay, VW, okay. So what we're having is now we have a V vector space, W vector space, and we're thinking of some function or map T now. We didn't say T is a matrix, right? Okay? We didn't say T is a matrix. We're just thinking of a function. Okay? There's a T map, T function, and we call this linear if two properties hold right there. Which is, the first one is that if you add two vectors and then transform it, like then if you map it, it's going to be same as if you do it separately. So, like there's a U and V here element. Let's say you did U plus V, which is also element here, right? There's a property of vector spaces. So you can do TU plus V. But what we can do is do it separately, TU, and just add it up in the end. And it gives you same answer. And also, the second one, which says T of CU is same as TU times C, right? So it's linear in the sense that you can multiply the vectors by scalar before the transformation, before the mapping, or after the mapping, okay? So you had V, U, you can do TU, and then multiply by C. Or you can multiply it beforehand. You can go CU first, and then go T. They're going to be same. And if there's a map that satisfies these two conditions, we call them to be a linear map, okay? Any questions so far? Okay, so you can basically see that matrix actually works a lot like T, because if you change it with T to be matrix, you can kind of see that matrix works a lot like linear map, actually. You can also see, you can kind of prove it later on, but you can kind of see also with the matrix, like if you do this, it's going to be same as this. So you can do addition separately later, or you can add the two vectors first, and then do matrix transformation. They're going to give you same number elements. And also, similarly, we also have, where's that? AX, C, and ACX. It's going to give you the same answer, right? We kind of see that actually matrix is just like a special case of linear map. Okay? I'm not going to talk too much about this. I just wrote this because it's a very important theorem. But I just said that linear map might not be a matrix, and said that matrix is a special case of a linear map, right? Because I said that right there. But actually, there's a fundamental theorem of linear algebra. We're not going to prove it, but what does it tell us is it's not really about the special case, actually. Actually, there's like a one-to-one correspondence. So what does that mean? So to be exact, I wrote here that like basically the definition of what fundamental theorem means. Basically, every matrix defines a linear map, and every linear map can be represented by a matrix. So what does that mean? So I'm not saying like matrix and linear map are like equal. I'm not saying that. But there's like a one-to-one correspondence. So what does that mean? So if you have any sort of linear map, it says T. What this theorem tells us is that for this T, there is going to be some unique matrix, A, that kind of is, in a sense, more similar to T. So basically, this process, linear map, is same to the process of A, okay? For T, there's some A. And also, inversely, for any matrix, this matrix represents some sort of linear map, okay? So in a way, if there's like a linear map world, and if there's like a matrix world, I'm not sure if there's a matrix world, but if there's like some set, okay? Although there has to be some conditions, but in this, what this is telling us is that there's some sort of like a one-to-one relationships. So for any sort of linear map, there's going to be some matrix for it. And the matrix, there's going to be some linear map for it, okay? So it's like a one-to-one correspondences. So in that sense, it's not really that linear map and matrices are in a relationship where matrix is like a special case of linear map. It's more like there's a one-to-one relationships there, okay? If you want to know more about this, you should like take some linear algebra classes or something similar. Although I'm not sure they talk about this too much in detail, though. Okay. All right. Let's go. And now for the end of the session, we're going to give you some very useful definitions you should know about matrices so that you don't get confused if you hear about this matrix and don't know what this means, okay? All right? So I listed them, and after this slides, I'm going to give explanation for every one of these terms, so what it means, okay? Starting from square matrix all the way to trace, all right? Okay, square matrix. In Korean, I think it's 정방행렬. If I'm correct. Although that might not be correct. But anyway, so what is square matrix? It's very simple. It's just when the matrix has same row and column. So n by n matrices. So if the matrix has same number of rows with columns, we call that as a square matrix, right? Because like square in Korean means like 정사각형. So like basically the matrix is like a square. It's not like a rectangle, okay? That's why we call this square matrices. And a lot of the time we use these square matrices a lot, especially when we're trying to find determinants and invertibleness in like economics and econometrics. So you should be very familiar with this square matrix, okay? All right. I did say we're going to talk about what diagonal matrix kind of means, so I'm going to give you a definition. The diagonal matrix is a lot more easier to understand. It just basically means that it only has elements in diagonal, okay? So you can see like the diagonal part. So, and usually when we say diagonal matrices, you mean like from left top to right top, right bottom. We don't go this way, okay? Normally, but usually we mean that. So basically what it means is that only diagonal elements have non-zero elements. And other than that, it should go zero. And we call these sort of matrices as, you know, the diagonal matrices, okay? So like pop question would be, although we don't really use this, this is also diagonal matrix, right? Diagonal matrix, this is diagonal matrix, this is one, or something like this. So as long as diagonal parts are non-zero, but it could be also zero, okay? And we sometimes say the term upper or lower triangular matrix. I don't know what it is in Korean. Maybe 삼각형열, I guess. 역삼각형열, something like that, I guess. So what this means is that basically we call that matrix a triangular matrix, or maybe triangle matrix. I'm not sure if what is the right definition, but we usually call that when it has only elements in the upper or lower parts, right? So basically, it's very similar to diagonal matrices, but instead of having only elements in the diagonal parts, it also could have elements either in the lower triangle part or upper triangle part right now, okay? So the example I put here, this, this matrix would be something called like lower triangle, right? Because there's like an element in the bottom parts. So something like this, okay? And very important matrix you should know is the identity matrix. So identity matrix, so what is it? So basically, we call this sort of matrix as an identity matrix, which is like A. So it's a diagonal element, but it has ones in the diagonal parts. Only one element, okay? There's like one for, there's number one in there in the diagonal parts. We call these kind of matrices as identity matrix. So what's so special about this identity? So what's with this diagonal matrix with one in the diagonals is that you can easily see that any sort of matrices you're going to get, if you multiply this identity matrix with B, with this matrix, you're going to get the matrix again, the original matrix. So what I mean is that, for example, like think about like, so this sort of example where you have this element, you do multiplication, you're going to get row column. What you're going to get is going to get 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So you got the same element. So what identity matrix does is basically it just gives you back the original matrix you multiplied it with. Okay? And this holds even if you put this here, or you put the identity element, which we kind of denoted by I here, okay? Doesn't matter, this. In this case, the order of the matrix multiplication doesn't matter, okay? But also be aware that like in this case, you usually say, in order to be, you know, you can kind of see that in order for the matrix to be same, it kind of has to be like a square matrix in this case. So when we usually say identity matrix, we kind of mean like a square matrices, okay? So the resulting matrix that we are multiplying will also be most likely be square, okay? So you can see that any sort of matrix you have, like B, if you do BI or IB, you're going to have B. Then we usually denote the identity matrix with a symbol I. So if you see some I, that means it's identity. All right. And also nice quality is that we have a transpose of a matrix. All right. Although I don't know the name for this in English, in Korean. So for some matrices, A, and sometimes we sometimes denote matrices like that, where you have a parenthesis in Aij. So basically what this means is that like basically it is like set of all elements where the values are indexed by ij's. Okay, we sometimes denote matrix like this, and transpose of a matrix is this. It looks all similar, except the index now switched. Okay, so we can kind of see that the row and the columns are going to change, right? So we have an element A here. So we see an A matrix here. And if we have its transpose, and for notation, we either use like the dash or T for transpose of a matrix. What we get is this element. Another typo. You know, like there should be like dash or T here, right? So you did a transpose of a matrix, and you can see that the diagonal part stays because even if you switch row and column, it's the same number, right? But for other parts, this part, 1 to 4, goes into here, right? Their row and column indexes switched. So that's the transpose of a matrix. Okay? And let's see. Oh. We also talk about sometimes when we sometimes say like matrix is singular or non-singular. Okay? So I just wanted to tell you what that kind of means when you say matrix is singular, non-singular. So what does that mean is that basically so we say that if columns of matrix is linearly dependent, we usually call the matrix to be singular. So what does that mean? Otherwise, we'll call it non-singular. So you know, matrix has many columns, right? Most of the time. Like in this case, there's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Think about like this matrix is, and you can kind of think of it as a combination of column vectors, because you can think of this like a vector, right? So it's like a 3-vector combined, and it made a matrices, and you can kind of think about these as U, V, W matrices, right? Because we can think about this in terms of think about these terms in terms of vectors, right? Vectors. So we can think about whether this is linearly independent or dependent, right? With these. So, for example, yeah. So if these are, and if you check them, and if these vectors, if they're linearly independent, we call this matrix as being non-singular, right? And on the other hand, if these vectors if they turn out to be linearly dependent, we call them singular. There's not much reason for why we call it that way. It's just like it's like a definition, okay? So that's why we do this. And usually, I'm not going to explain too much in detail. And the reason why we want to check this is that by some theorem and definition, we can kind of show that if the column vectors are linearly independent, the matrix becomes invertible, which we'll talk about later. And if it doesn't, which means if the vectors are linearly dependent, they're not invertible sometimes. So in this, because there are some cases like that, we can use it to show that whether a matrix has an inverse or not, okay? I'll talk about this later on, okay? So when you see a term where it says like there's a singular matrix or like non-singular matrix, it kind of means that it means about the column vectors, that they're not linearly dependent or independent sort of way, okay? All right. We talked a bit about invertible, so we're going to talk about what invert means. Okay. When we say matrix is invertible, is that if for some matrix A, there's an invertible matrix, we denote it by A minus 1, okay? That's just a notation for an invertible matrix. If there's an A minus 1, such that if we multiply the A minus 1 with A, you're going to get the identity matrix, okay? And this one also, the switching, it doesn't matter. So if you have an element A, and if you have A minus, multiply it, and if you get the identity matrix, then we call this sort of A minus element, A minus matrix as invertible, okay? And now you realize why we talked about the non-singularity, because we can use this kind of to show whether the matrix has an inverse or not. And if it does have an inverse, it's a very nice quality, because although we're going to talk about it, let me give you some reason why invertibleness is very important. It's because remember like the equation where we had this? Like you're solving a mathematical or economical question, and you have multiple equations. And suppose that you have some case where you can write your equations into one line like this. So you have the y variable, you have a variable, and you're wondering x, right? Then the thing is, if you can use the invertibleness, if a is invertible, what this means is that you can multiply each side by a invertible to get this. Then what happens is this side becomes identity, right? So this kind of disappears. So you get the answer to the x, right? You can calculate the x. And this is unique, right? But there are cases where the a is not invertible. So there's no such thing like this. Okay? You cannot find it. Then probably what this means is that your equation is a case where there could be multiple solutions, right? Okay? In that case, there will be no unique solution to it. So it kind of shows that whether your overall equations, whether it has a unique solution or not, you can kind of check it by implicitly using to check whether there's invertible matrices, okay? All right. Okay. And something about the orthogonal matrix. So orthogonal is nothing that difficult. It just means that by definition, A transpose is same equals to the A inverse. Okay? So what does that mean is that we can kind of mean what it means. So basically, we are saying that A inverse is just transpose of an A, right? So why is it important? It's because remember that A inverse, the quality was that if you multiply A with A inverse or A inverse with A, you're going to get the identity matrix, right? But because inverse of a matrix is the same as transpose, we just can write this as this, right? And it's a lot easier because I didn't tell you explicitly about how to calculate the inverse, but sometimes getting the inverse matrix is very hard. So most of the time, if a matrix is orthogonal, it's very nice because we don't need to find inverse. We just need to just use a transpose. That's the inverse. So you just use it to calculate the inverse, right? That's why it's very useful. All right. Moving on to the last part. Yep, trace. I'm just going to explain what trace is, like literally the definition, in case you see them. So trace, what it is, just that it's sum of all diagonal elements. So you're going to have a matrix, and what it is, like there's a matrix, like 1, 2, 3, 1, 2, 1, 1, 0. And if someone asks you what's the trace of this matrix, is that, or I mean, basically in definition, it means just sum of the diagonal elements. So it should be 3. Okay, so, and it's also something used in definition or sometimes proving things, so you should know this. That's why I put it here. And, okay, this is the end of the session. And because we don't have a few minutes left, we're going to continue with the next session and just end a bit early, I guess, like 40 to so much, okay?